this is a continuation on Koszul complexes. Okay. So now for this we can assume that R is non-negatively graded, finitely generated over R0, which is a field. 0 equals K, a field. Finitely generated over algebra over a field. Okay. So we can extend the same construction from last time to get Koszul complex K of F1 through Fr on M, where M is a graded module. And F1 through Fr are homogeneous elements of positive degree, not units. Okay. The thing is, we start with K of F1 M as 0 to M to 0 multiplication by F1. This is in position 0 and this is position 1. And then we just define inductively K F1 through Fr M to be the mapping cone of the map in which we take R minus 1 of them and multiply. So if you just go back and do the same thing, the complexes in this will be just direct sums of M with itself. Okay, and therefore we can talk about multiplication by Fr and then this. So the cone of this map, we can define it like this. So it's entirely analogous construction, just repeating whatever we did. Okay. So now we want to prove, want to describe an important use of this this Koszul complex. Okay, so just to remind ourselves, F1 through Fr are homogeneous non-units, so positive degree. M finitely generated. Then the following are equivalent. 1. F1 is a non-zero divisor on M, and for all I between 2 and R, Fi is a non-zero divisor on M mod F1 through Fi minus 1 times M. Okay, so this is one condition. 2. The homology of the Koszul complex on R elements, Koszul complex of M, all these R elements, is 0 for all I different from 0. This is the thing. Just a remark here, H naught of the Koszul complex. So let me just put an underscore here to denote F1 through Fr. This Koszul complex is just M mod F1 through Fr times M. And this is not 0 because by Nakayama's lemma. I mean, an ideal of elements of positive degree cannot kill a module. I mean, M cannot be equal to I times M if every element of I has positive degree. Okay. So this is what we have. Okay. So let's prove this. I mean, we will only give a brief sketch going back to the previous lecture, the last lecture, in which we considered Koszul complex as a mapping cone of, in which we said that the mapping cone constructs the homology induced by the map. Okay, so what does that mean for us? So proof of the proposition. So we have this Hi of k f1 through frm. This is the cone. Okay. On this side is Hi minus 1. So if you work out through the cone, this is what we will have, of k with one fewer element. All this is for the complex M. Remember, the two pieces in the cone are will have one fewer element. Okay, and this is multiplication by Fr. 2 Hi, same module. Maybe I should just. Okay. Let's write this thing. So we have Hi of k of all the elements f1 through frm. Okay. To this comes the map from the G. Okay. But G was also k, this one. K f1 through frm, fr minus 1m. So the G and the f have only f1 through fr, the r minus 1 elements, while the cone will have all r elements. So this is the cone, and here is the same thing, Hi of k f1 through fr minus 1, and this is multiplication by fr. And here is the same, this is for all of them. So after this would be Hi minus 1 of k for r minus 1 elements. I mean, it will appear twice. Okay, and this is multiplication by xr. So this is what the homology is. Okay, so the proof will go by induction in one direction. So assuming proving 1 implies 2, okay, we just have to, we will prove, so this will prove. So in 1 implies 2, we can assume that the statement is true for r minus 1, sequence of r minus 1 elements. Okay, so 1 implies 2 by induction. Okay, so one has to consider two cases separately. Okay, because after Hik is Hi minus 1. So whether if I is 1, this is 0, but that doesn't vanish. Okay, so okay, by induction we can assume that Hi of k f1 through fr minus 1 on M is 0 for all I different from 0. Okay. So then, okay, so if I is at least 2, then we have H2 here, H1 here for fewer elements, which is 0 by induction, and H2 for fewer elements, which is also 0 by induction. So therefore, for all I greater than or equal to 2, Hi of k of r elements is 0. Okay. And we have an exact sequence . 0 to, so the last part, if I is 1, then this is 0 by induction. So 0 to this to H0 to H0 to H0. H1 of k of r elements to H0 of k of r minus 1 elements. Then this is multiplication by Fr to H0 of k of R elements. Okay. But what is this? This we observe that H0 is just M mod the sequence, multiplication by FR, but that is injective. That this is a non-zero divisor. Therefore, by 1, sorry, okay. I mean this is this is same as this. This is injective. Therefore, by 1, H1 of K, F1 through FR, M is also 0. The other things we are already checked. Okay. So this is the one direction of the proof. In the other direction, we are assuming that for positive I, this is 0. Okay. So therefore, so this is 2. 2 implies 1. Okay. Since Hi of K with R elements, so this is 0, we get surjective maps from Hi of K with R minus 1 elements to itself. So that's what the first map here is. Okay. This is 0, so we get a surjective map. I mean, it is also injective, but that's not really relevant or useful at this point. Okay. This is multiplication by FR, but this is surjective map. Okay. But again, Nakayama lemma comes in. But since we are handling only graded thing, it's much easier with the graded Nakayama lemma. So which means that F has positive degree. So a generator here is a multiple of something from here of previous degree, but in previous degree there is nothing. So this, by Nakayama lemma, this says that Hi of K, F1 through Fr minus 1 M is 0. Okay. But even if we were working in a local ring, all of this would have gone through. Even here, this would say that a module is something in maximal ideal times itself, and hence it is 0. Okay. So this is, in either case, Nakayama lemma will be useful, either in the local case or in the graded case. It is just much easier to follow it in the graded case. Okay, so this is the this is one characterization of of what does it mean to say that all Koszul homologies vanish. Okay, so then we just want to quickly make some remark. So corollary with F1 through Fr satisfying. Okay. So let's just say, let's just say definition. We say that F1 through Fr is an M regular sequence, or a regular sequence or regular sequence on M if it satisfies the conditions of the proposition. Let's just say condition 1 of the proposition. We'll take that as a definition. Okay. So then corollary, if F1 through Fr is R regular, then the Koszul complex on F1 through Fr is a minimal graded free resolution of R mod F1 through Fr. Okay. So this is because with this hypothesis the other things vanish and they only thing that we need to observe, which we have already done once, is H0 of the Koszul complex is this thing. Okay, so we have a complex of free modules, graded, degree preserving, all that is satisfied. The homologies in position 1 to the left are all 0. At the 0th position, this is the homology. Okay, so it is a resolution. And now we can go back. We worry about the polynomial ring now. Okay. I, an ideal generated by a subset of the variables. Okay. Let's just say xi1 through xic, where I1 less than I2 less than IC. Okay. Then R mod I, the Koszul complex, K on xi1 through xic is a minimal graded free resolution of R mod I, and it has length at most, it has length exactly C. Okay. So this is, okay. And now therefore we can prove it for all monomial ideals. Therefore we can prove it for all monomial submodules of free modules. Then once we learn how to degenerate from an arbitrary submodule of a free module to a monomial submodule, we would have proved Hilbert's Syzygy theorem. Okay. But there are other proofs, and most textbooks will discuss some other proofs. We just want to define, just to become familiar, the projective dimension of M dimension dimension of M is the length of the shortest free resolution of M, or in other words, in the graded, we are discussing in the graded situation, that is supremum of I such that beta I j of M is not 0 for some j. Okay. Definition can go for any ring, any Noetherian ring, non-Noetherian ring. It doesn't really matter, but for arbitrary graded rings, we can treat it as this. For we will have to allow for a supremum. For polynomial rings, the supremum is actually can be replaced by a maximum, because Hilbert's Syzygy theorem says it cannot go beyond n. Okay, so we can do this definition, and so we won't do anything with this. So in the next 2 lectures, we want to discuss another invariant coming from the graded Betti numbers. These things. Remember, this was just the number of copies of R minus J in Fi. This is the free part, the ith module in the free resolution. Okay, so this is what. So we'll do some exercises with this, but we will not discuss this any further in this. I will not lecture any more on this. Okay. So in the last 2 lectures would be about what is called Castelnuovo-Mumford regularity, and we will see how it's used in the first lecture. So in the next lecture, we will see how it's used to understand how it's related to Hilbert functions, and in the final lecture, we will use it to understand a problem in geometry which is stated without any reference to any of these techniques, but it will come useful at that point.